The next talk will be about the semantics of PROMELA, and it will be given by Byoungho Son. Sorry. Teach me how to pronounce it.
Okay. Thanks for the introduction. My name is Byoungho Son at POSTECH. Today, I'm going to be presenting our work on formal executable semantics of PROMELA, which is a very widely used model checking language. And this is joint work with Kyungmin Bae. So I guess many of you have heard of the SPIN tool because it's a very widely used tool for modeling and verifying concurrent systems or distributed systems. So PROMELA is the input modeling language for the SPIN model checker. So the workflow is that SPIN takes PROMELA code as input. It parses that code into an automaton, and SPIN performs LTL model checking on top of this automaton. Some good things about SPIN is that SPIN works fully automatically and very efficiently. And another good reason to use SPIN is that it provides a very intuitive high-level modeling language, PROMELA, which has a very similar syntax to C. So it's going to lower the hurdle for modeling for those who's already familiar with C. And so the tandem of PROMELA and SPIN has been very successful in the past few decades. It has been used in many real-world domains like cryptography protocols, Linux system calls, and many others. And the SPIN tool has received ACM Software System Award in 2001. However, there are limitations as well. The one problem is that SPIN only supports explicit model checking, which basically means that SPIN performs model checking by enumerating all the reachable states of the system. And therefore, it cannot verify properties for systems with infinite number of states. And this is very hard to remedy with deductive reasoning because there is no prior work for formal semantics that is aimed at code-level deductive verification. There are a bunch of work that provides the semantics, but most of the work focuses on translational semantics that translates PROMELA into the automaton. So all the high-level constructs of PROMELA gets parsed away. So PROMELA has no role in the analysis stage, which misses out a lot of opportunities to exploit state-of-the-art program verification techniques on top of PROMELA. So to overcome this limitation, our goal is to define an executable semantics of PROMELA. So by executable semantics, I mean a semantics that is almost like an interpreter by itself, so that you don't have to implement yet another interpreter. And then with this executable semantics, we aim to mechanize the semantics in a machine-readable framework. This will enable automatic generation of related tools like model checkers, state space explorators, and many others. In particular, we're interested in deriving a code-level deductive verifier for PROMELA programs. And hopefully, this will enable a wider range of analysis of existing PROMELA models used in the industry and academia. So to give you a little background of PROMELA, as you see in this example, PROMELA code consists of declarations for concurrent processes. So here you have the declaration for P1 and P2. And at the top of the code, there are declarations for the channels and integers. And there are two types of channels in PROMELA. One is handshake channel, and the other one is buffer channel. So for example, in this code, P1 is the sender of the handshake channel, and the process P2 is the receiver of the handshake channel. And this handshake channel is meant to be executed in synchronization, so the two operations are executed at the same time. On the other hand, there are buffer channels. So P1 is the sender, and P2 is the receiver. And in contrast to handshake channels, the sender does not have to wait until the receiver is available, and vice versa for the receiver. So this buffer channel is used for asynchronous communication between the two processes. So the intended behavior of PROMELA program can be understood as execution traces, which are sequences of atomic actions like channel operations. So an example of execution trace may start by the process P1 that sends a message to the buffer channel D, followed by process P2 that receives the message from the channel. So it's going to receive the message that is sent by the process P1 in the prior step, and then execute the remaining fragment of code, so on and so forth. So up to this point, we have this interleaved sequence. One exception is that of handshake channels. So handshake operations are meant to be executed at the same time. So this is the intended behavior of semantics, behavior of PROMELA at the language level. And one more remark that I want to make is that each of these basic actions are meant to be executed atomically. So for example, this increment statement is meant to be executed atomically, which is not necessarily the case in other languages like C. A PROMELA code may contain nondeterminism, like the if statements and the do statements in the code. So if statements are for non-deterministic selection, and do statements are for non-deterministic repetition. So essentially, do statements are repeated if statements. And this kind of constructs can also be found in many other related formalisms like Dijkstra-Scotted command language and many others. And another central notion is that of enableness. And enableness is really important because it determines when a certain statement can be executed, and it also determines when a certain non-deterministic branch can be selected. For example, to check if this second option of the outermost if statement is selectable, you have to check whether the guard, which is the whole do statement, is enabled, which again is reduced to the individual enableness of the inner structure. So in particular, you have to check the enableness of the, for example, the channel receive operation. And this is the channel receive operation via the handshake channel. So you have to ask whether there is an enabled matching partner in some other processes. Okay, so this shows that checking for enableness is quite complicated. And so we're essentially doing a proof search over each non-deterministic point and for each concurrent process. And it involves a very heavy computational, conceptually computational steps for doing the proof search before checking whether a one-step intended execution may be fired. So the problem is that this kind of proof search steps gives rise to this strict dichotomy between structural rules and operational rules, where the structural steps in the vertical axis corresponds to implicit proof search steps, and which is not captured by the operational steps intended by PROMELA at the language level. The reason why this is problematic is because the operational steps does not specify concretely how to perform the proof search. So this is problematic when, as far as executable semantics is concerned. So the challenge is to design an executable semantics that is as concrete as an interpreter, so that you don't have to implement yet another interpreter. And this kind of executable semantics will not include any structural reasoning for each one-step execution. So it's going to be flattened like that. And our approach to tackle this challenge is to represent PROMELA programs as continuations of computational tasks. And this approach is inspired by continuation-based semantics, where typical sequential programs are flattened into sequences of computational tasks so that every internal computational steps are represented explicitly. So this kind of continuation can be read as first do the step A, and then do the step B, and then do the step C, and so on and so forth in the linear structure. So our approach is to generalize this representation for computation so that the continuation can be forked to capture the non-determinism in each process. So here, each of the computational tasks may encode the proof obligations as special cases. Further extending this approach, we can also represent the non-determinism under concurrency. So a system of concurrent processes with non-determinism can be represented explicitly as a forest of forked continuations, where trees correspond to concurrent processes, and each of the branch in the forked continuation corresponds to individual non-deterministic options in the if statement. So this will correspond to a whole specification of the PROMELA program. So based on this representation, we proposed a semantic pattern called load and fire, which captures the interplay between the steps for proof search and the steps for actually firing the execution. So the loading rule defines how to perform the proof search. So for example, if we have this if statement, the proof obligation for the if statement at the leaf of the continuation, the load rule will decompose that proof obligation into multiple proof search sessions and explicitly represent it in the representation level. And then fire rule comes into play. It's going to discharge each of the enableness condition at the leaf. And at the same time, it's going to fire the side effect. One example of such side effect is that of making a non-deterministic choice, so that when the fire rule applies, the forked continuation gets collapsed back into the linear form, which reflects the fact that the non-determinism has been resolved. So let me give you a concrete example. First, the loading rules can be used to define the semantics of if statements, where the loading rule for if statement says if we have this proof obligation at the leaf of the continuation, what you do is you simply decompose this proof obligation into two separate proof sessions, where the upper one corresponds to one particular non-deterministic option in the if statement, and the proof session at the bottom corresponds to the rest of the options. And similarly, we can also define the semantics of do statements, which is non-deterministic repetition, by a load rule that says if we have this proof obligation for do statements, what you do is you simply attach to it the state, another proof obligation for the if statement. So this kind of description is this coincides with the imperative interpretation of do statements, that do statements are basically repeated if statements. So to demonstrate how these load rules and fire rules work together, here's a concrete example. So this snippet of code is the one that we saw in the previous example for the process P2. So initially, the outermost if statement will be represented as a proof obligation like this. So this is a continuation of the initial state. And then the loading rule will apply to the if statement, so that the continuation will be forked like this. So the upper branch will correspond to the branch 3 in the code, and the lower proof session will correspond to the whole do statement in the code. Now, the loading rule for the do statement will apply, which simply attach in front of it a new proof obligation for the if statement. And again, this will be decomposed by loading rule to decompose further, like this. And now we have all the proof obligations decomposed. So if you assume that the buffer channel D is non-empty, which means that that the channel receive operation at the leaf node is enabled. So this is the timing where fire rule comes into play. So it discharges the proof of this atomic action, and at the same time, it makes a non-deterministic choice, collapsing the continuation back into the linear form. And as another example, this is the complete version of the previous example, where we have two concurrent processes. So the two concurrent processes will be represented as the forest of two continuations initially. And by sequentially applying the load rules in the fully loaded form, the forest will look like this, where each of the branch is decomposed. And the result is that now it is clear from the context of non-determinism that the handshake operation is enabled. So this can be checked by the fire rule by a simple syntactic matching. So you don't have to go through structural reasoning at each step. So the fire rule comes into play. It discharges the pair of proof obligations, and it makes non-deterministic choices over the pair of continuations. Now, to summarize our approach, our pattern of load and fire, we had these loading rules that bring the proof search explicitly represented into the semantics level. And then the fire rule will fire without structural reasoning because it's going to be, because the structure has been flattened by the loading rule already. So alternating the two stages step by step will give us the executable semantics as desired. So based on this semantics design, we mechanized our semantics of PROMELA using the K framework, which is a semantics definitional framework based on continuations. And we formalized most of the core features of PROMELA in the K framework. And it turns out, by design, semantics in K is highly executable. And the K framework exploits this executability to automatically derive related analysis tools like model checkers, deductive verifiers, and many others from the semantics. And it has been used to successfully specify the semantics of many programming languages like C, Java, and so on. And in particular, we used the model checker given by K to empirically validate our semantic definitions of PROMELA by comparing the outputs obtained by the original spin implementation and the model checker. And again, we used the deductive verifier given by K to formally verify PROMELA programs. So our case study includes using this deductive verifier to formally prove invariant properties for distributed systems. And it turns out sometimes the deductive verifier obtained by K can be more powerful than spin is. And we demonstrated that this is a case for proving mutual exclusion for Lampert's bakery algorithm, which has an infinite number of reachable states. And as a result, this example is not verifiable by the spin model checker. But this is verifiable by our deductive verifier. So Lampert's bakery algorithm is a distributed mutual exclusion algorithm proposed by Leslie Lampert. So this is the code of bakery algorithm written in PROMELA. So we have two declarations for processes. And each process goes through 3 stages. So first, each process gets the ticket from a global counter And as a next step, when the ticket number gets called, it gets into the critical section. And then after that, it can exit the critical section non-deterministically, and it gets repeated over and over. The result is that the ticket number can grow indefinitely, inducing an infinite number of reachable states. So Spin cannot verify this PROMELA program. And we verified the mutual exclusion for this bakery algorithm using deductive reasoning. So we annotated the bakery algorithm code with preconditions and postconditions. So under a reasonable precondition, our postcondition asserts that asserts the invariant that the number of processes in the critical section is always less than or equal to 1. The result is that the deductive verifier by K can automatically verify the specification within 5 minutes. As a side note, we used some auxiliary specs to aid the reasoning for the deductive verifier. So to conclude my presentation, we designed an executable semantics of PROMELA, which is enabled by the semantic pattern, load and fire, based on the forked continuations. We mechanize the semantics in the K framework, which opens the door to code-level deductive reasoning for PROMELA programs. And also, we demonstrated that our deductive verifier can verify systems with infinite number of states, which is out of Spin's capability. Future work includes extending this deductive reasoning to temporal properties like LTL logic, which is outside of which may be outside the scope of the invariant properties that we covered. Another interesting direction would be to extend the case study for parametric models to allow arbitrary number of processes. Okay, so this is the end of it. Thank you very much.
So there is place for some questions. So please, Anton.
So maybe just a quick question. So can you also do liveness now, or just?
You mean liveness?
Yeah. Can you also verify liveness now?
Not yet.
I mean, not really.
Yeah, we cannot do a temporal logic yet, so
Okay,
it's
so
a future work.
You can't really do it yet. All right. Okay.
Okay.
Yeah.
Other questions? I have one by waiting for that. So you say that you have this project of doing parametric verification, but I mean to introduce infinite number of parameterized number of processes, for instance. But you have sometimes in deductive verification, there were some work on reducing the parametric problem to some finite problem and
like
so on.
cutoff techniques.
Yes, so
like
taking the small model or thing like that. So will you think that it will be possible to do these such proofs in our system somehow? Because
I'm not so sure about that because we haven't really started that, but I think that would be a very good. Because
you have already the deductive verification engine somehow for the computing these traces, so then you have only to.
Actually, our proof system for this deductive reasoning is based on what's called reachability logic, which is a particular proof system by the K framework. So I'm not really sure if that allows that. So we'll have to look to that.
Okay, other question?
Just one more question. So do you have any other example other than this bakery protocol, or is this the only one?
This is the only non-trivial example. We have some trivial examples, but yeah, this is the only non-trivial example covered in our paper.
So for the bakery, you mentioned that there were also some auxiliary specifications. So can you elaborate on that? What exactly did you need to provide in addition?
Yeah, so this has to do with the fact that the reachability logic, which is the base, the proof system that this deductive verification is based on, and auxiliary claims are only of technical interest. So I think in principle it works automatically at the conceptual level, but the framework, the toolchain of K-framework, it does this deductive reasoning by somehow enumerating symbolic states. But the problem is that it does not maintain all the intermediate states by for efficiency issues, memory issues. So these auxiliary claims is to somehow it's related on the fact that how to say, the reason why we have to use this auxiliary spec is because the implementation of this deductive verifier does not maintain the internal states. If it maintains it, then we don't need it.
Okay. And maybe one more question. So you assume, so in your bakery example, so you assume the counters to be unbounded precision, or is there? I'm not an expert in PROMELA, but I thought there is some like bound on the size of the integers or something like that.
In the syntax of PROMELA, there's you cannot specify for arbitrary number of processes, but yeah, we have to relax the syntax in order to do that.
Yeah, but about the precision of the integers there, because you have the counter, right? You have so if you have bakery, you have somebody who is counting the current ticket, right?
Yeah.
And then, like in PROMELA, is the integers there are bounded size, isn't it?
Yeah. In PROMELA, it works like that.
So is the bakery does it take care of the overflow or underflow or something like that?
Actually, that's the issue that when we're using the spin model checker. But because we're not using the spin model checker, we're not interested in that.
So you still have time for one question? Okay, so I have one. So there are other attempts to give formal semantic for PROMELA, for instance, in Isabelle and
yeah, I know that. Yeah.
So how you compare with this work, for instance?
Isabelle.
Hall.
So if I'm correct, that work is about translating PROMELA into automaton using Isabelle.
So it's foundation, yes. So the semantics, it's also semantics of PROMELA.
So the semantic style is really different.
The translation, it's okay.
Yeah. So we're not. So it's directly translating the PROMELA model into an automaton. So yeah, the PROMELA constructs are parsed away. Yeah. So, but yeah, so we cannot apply code level deductive verification on top of that. Yeah. So that is the problem.
Okay. So let's thanks the speaker again.